ต้องเป็นตื้อต้องมาสีดีนะใช่ดีกว่าตัวชุดก่อนแล้วกดในขวดขนาดต้นวิดีโอซูมที่เดิมเนี่ยมันนิ่งอยู่ตรงนี้
นะครับให้สำหรับทุกท่านได้เขียนคำถามนะครับเพื่อที่จะได้ถามท่านโนเบลที่จะพูดในวันนี้นะครับโดยเจ้าหน้าที่ของเราจะดำเนินการเก็บนะครับกระดาษต่างๆนะครับที่เป็นคำถามจากท่านทุกคนนะครับ Ladies and gentlemen, welcome to British Dialogue Toward Culture Peace. May I ask you to not use your mobile phone during the presentation. Also, we have given you a piece of paper to write your question so that our staff can collect and bring up to the stage so the Nobel Prize winner can answer your questions. Thank you very much. It will begin at 2 o'clock. งานจะเริ่มเวลา 2-4 นาฬิกาครับขอบคุณครับ Welcome to our special lecture entitled Laser Technology in Peace and War by Professor Nicolaas Bloembergen, a Nobel laureate for physics. First of all, may I call upon Assistant to the President of Chulalongkorn University, Professor Nicolaas, on behalf of the President, to give a welcome speech.
Honorable Professor Nicolaas Bloembergen, Chairman of the Board of Directors of International Peace Foundation, representative of Kasikorn Bank, ladies and gentlemen, I am honored to welcome all of you today on behalf of Chulalongkorn University to the lecture series entitled Bridges, Dialogues Towards a Culture of Peace. This lecture series was launched with the awareness that peace is a notion more pressing than any other for nations, communities, and individuals. We are therefore faced with the challenge of incorporating more meaningful dialogue into our lives, not only to promote human security, but also to create a culture of peace and understanding. As a Nobel laureate for physics and a pioneer in the field of nuclear magnetic resonance, quantum electronics, nonlinear optics, for which he shares the distinction as one of the founders, and lasers, Professor Nicolaas Bloembergen stresses how developments in science can play a crucial role both in peace and in war. We relish the opportunity not only to welcome a world-renowned scientist to Thailand, but also celebrate an occasion when fellow Thai scientists and educators from multidisciplinary backgrounds may learn from the expertise and insight of a person who has devoted his entire career to the pursuit of scientific progress in order to achieve a better quality of life of all human beings. I would like to take this opportunity to express my sincere appreciation to the International Peace Foundation and the Kasikorn Bank, which have helped make this wonderful series possible. Professor Bloembergen will be joined by other Nobel laureates in peace, physics, chemistry, and literature, as well as decision makers in international politics, economics, science, culture, and the media. For today, once again, may I thank our distinguished speaker for giving of his time, and I feel sure that I can speak for all members of the audience when I say that we will certainly learn much from the lecture we are about to hear. Thank you very much.
Ladies and gentlemen, friends, I have no concept for peace and no solution how to achieve peace. But I know that the first step towards peace is dialogue, and the first step towards dialogue is respect. The International Peace Foundation doesn't take sides, but acts as a mediator by creating an independent platform for dialogue where people meet who normally don't meet, people from all walks of life, people who speak different languages, even if they use the same. As politicians speak another language than artists, and business and religious people another one than scientists, it is seldom that they speak with each other or even work together. We live in a world where some people pretend to know the answers and solutions, how to solve problems, how to achieve peace, though the quest for peace lies in the art to pose the right questions. The International Peace Foundation believes that the problems of the world cannot be solved only by politicians, only by the economy, only by scientists or religion alone, but by working together. This is why in the event series Bridges, Dialogues Towards a Culture of Peace, people from all walks of life meet in a multidisciplinary program to find creative solutions to solve problems and to achieve peace. Peace within yourself, within your family, peace within social structures, peace with nature and the environment, peace between nations, cultures, and religions. Peace is a process. Dialogue is a process. It is nothing which is achieved instantly. It needs time. This is why Bridges is not organized as a single conference and then everything is over again and forgotten, but as a series of events over the period of 1 year in which 24 Nobel laureates build bridges with Thai leaders in all parts of society and with the general public. After the first 20 events of Bridges, which attracted 8,000 participants in November alone, we have been approached especially by students and young people who have been inspired by the content of the events and who want to actively participate in this dialogue process towards peace, which is not something which can be left to the elite of a few, but which needs the participation of everyone. This is why we want to further encourage your input and your support, and why we look forward to your questions and suggestions, your advice and guidance in this dialogue process towards peace. I thank the chairman of the Thai Advisory Board for the event series Bridges, His Excellency Anand Panirachon, Kun Bantun Lamsam and Kasikorn Bank, Professor Thakchai Sumit and Chulalongkorn University, and all sponsors and partners for our fruitful cooperation, and especially Professor Nicolaas Bloembergen, who came to Thailand without any honorarium to support the events, and I now look forward to the keynote speech and his important contribution to build bridges. Thank you very much.
Assistant to the President of Chulalongkorn University, Professor Jalurat Tantrathorn, Chairman of the Board of Directors, the International Peace Foundation, and distinguished guests. In celebration of humanity without border and in the administrations of Thailand as a peaceful country, Kasikorn Bank is proud to sponsor speeches of 22 different Nobel laureates for the next 2 years. Each Nobel laureate will deliver his or her notes addresses in Thailand as part of the International Peace Foundation's Bridges Dialogue Towards a Culture of Peace project. On behalf of Kasikorn Bank, I am honored to present Professor Nicolaas Bloembergen, the winner of the Nobel Prize for Physics in 1981. Welcome. Thank you.
our guest of honor, Professor Nicolaas Bloembergen. Professor Nicolaas Bloembergen is a professor for physics who received the Nobel Prize for Physics for his contributions to the development of laser spectroscopy in 1981. He was born in the Netherlands in 1920, studied at the University of Utrecht, and obtained the doctorate degrees in 1943. After the Second World War, he came to America and started to work at Harvard University in the field of nuclear and electron paramagnetic resonance. Later in quantum electronics, microwave lasers, nonlinear optics, of which he is one of the founders, and also lasers. This started a lifelong association with Harvard, which continues to the present day. In 1948, Professor Bloembergen returned briefly to Holland to receive a PhD degree from the University of Leiden for his thesis on nuclear magnetic relaxation, which became the classic Bloembergen, Pound and Purcell paper, BPP, in the Physical Review of 1949. Professor Bloembergen received various awards such as the Medal of Honor from IEEE in 1983 for the invention of the three-level laser, and he is a member of numerous professional societies. Until present, he is Professor Emeritus at Harvard University and since 2001, Professor at the Optical Science Center at the University of Arizona. Ladies and gentlemen, please welcome Professor Bloembergen.
Thank you very much. Good afternoon, ladies and gentlemen. I'd like to talk about technology which is known as laser technology and give you a historical overview of various aspects of this technology and how it contributed mostly to peaceful purposes and also to war purposes, which we shouldn't ignore. In fact, the first laser was demonstrated in 1960, 43 years ago. And the word laser stands for light amplification by stimulated emission of radiation. Clearly, the origin of the word laser is the English language. But the remarkable thing is that the same word is used in most other languages, and even the Russians, already at the height of the Cold War between the Soviet Union and the United States, used the word laser in the early 60s. And so you see, there was scientific communication at all times, also between Soviet scientists and United States scientists, and of course also scientists of other countries. Now I'd like to start with a few basic physics ideas and of why lasers are so different from ordinary light sources. Most of the light before lasers was due to a process known as spontaneous emission. Light occurs because of atoms of electrons in atoms or molecules can occupy certain orbitals, and the bigger ones have a higher energy, and they can fall down to a lower energy, and as they fall down, they emit a particular light quantum or photon. And this is the cause of the origin of light. But there is one other process, two other processes, besides spontaneous emission, and one that occurs most frequently is absorption. Can we try this one? Yeah, there we are. If the electron is originally in a orbit of low energy, it can be raised by absorbing a photon from the incident beam and to get it excited. So we have spontaneous emission and absorption. What is stimulated emission? It's the opposite of absorption. You have the electron in an orbit of high energy and you shine more light in, and then this induces the electron to fall down and add a photon to the beam, so you get amplification of light. And in order for the stimulated emission to overcome and be dominant over absorption, you have to have clearly more electrons in the orbit with higher energy than the orbit with lower energy. And that is normally not the case. Any material in this room is usually absorbing because you have more electrons in the lower energy than in the higher energy. But this is the essential condition to get laser action, that you have more electrons in the orbit with higher energy. And how do you get them there? By a pumping mechanism. And that is the essential basis for laser action. The electrons are then used to amplify the light wave. And the difference between spontaneous emission and stimulated emission can be compared to a coherent process, which is the stimulated emission, and an incoherent process. You see, these are people walking in a marketplace or at a fair, and they all walk in different directions. But compare that to a military column with marching music, and all the people walk in step. And the same thing happens to photons by stimulated emission. They add to the light that is already there. So here you see how this process takes place. You have a material with electrons, atoms, and initially you get spontaneous emission in all directions, but then all the atoms are forced to contribute to this photon that travel normal to these two mirrors, and that builds up as an avalanche, and eventually all the electrons put their energy in that particular light wave defined by the mirrors. Now that is all the basic physics you have to know. And here you see the arrangement of Mayman in 1960, the so-called ruby maser. Here is a ruby crystal, and you have parallel mirrors at the end. And now you have a pump mechanism provided by this xenon photographic flash lamp, and you force all the energy of the electrons in the ruby. Those are the chromium ions in the sapphire crystal to emit in that one particular direction. This laser action can also occur in mirror media. This is the second earliest laser. That is the helium neon laser, which is a gas, but the same type of process happens in that case. Now, why is it when you get this coherent emission due to stimulated emission, you get laser characteristics? All the atoms emit at the same frequency of the light that is already there. They all move in the same direction, all the photons, and you get a high degree of directionality. And you therefore consequently also get a very high intensity. And it's these three properties of lasers that make them so different from ordinary light sources. And it is possible to concentrate that light of a laser, just as any other light, that we're concentrated in space by a lens, and in time by forcing the stimulated emission to come out in a very short time. And then you get such high light intensities that even from these first small ruby lasers, if you use a lens objective and you focus them in air, you get a spark, because the amplitude of the electromagnetic field is so high that you ionize the material. In fact, in the very early days, and this is a joke, the ruby laser pulse could penetrate a number of Gillette blades. And rather than talk about intensities in watts per square centimeter, people said, wow, my laser has a strength of 5 Gillettes because it drilled holes through 5 Gillette blades. And of course, this suggests a military application, that the directionality of the laser light, you could send these blobs of electromagnetic energy possibly to an incoming missile. And they called that the incredible laser, which was used in the first James Bond movie, Spy 007, and they used their lasers to break into a safe and so on. But the military wanted to use it for missile defense, and here you see the incredible laser. Well, of course, because of this potentiality, the military supported a lot of the original laser research. But I can say that even to this day, this application of lasers has not been materialized. It is just too difficult technologically to achieve that. And I served on a committee in 1961, and I learned that in order to hit a missile, intercontinental missile, you had to deposit 1 million joules of energy onto that missile. And that would drill a hole in the wall and the missile would fail. And I pointed out that this little ruby crystal of 1 cubic centimeter emits 1 joule of light, and therefore it could penetrate 4 Gillette blades. But if you multiply that a factor of million, you would take a cubic meter, which is 1 million cubic centimeters of neodymium glass laser, and you would get 1 million joules of light out. This sounds simple on paper, but in practice, this is very hard to achieve and to control that amount of light energy. And even today, it is very difficult to do. So this application, which is indicated by the popular magazines and newspapers in the early 60s, is still not a reality. Credible lasers inside are much smaller and lead to much more beneficial applications. And let us now briefly review those. One of the first applications uses this directionality, as in this light pointer, and it was used to construct a subway tunnel into San Francisco Bay, and a helium neon laser was used to align these tunnel segments, and that was in the late 60s. And here you see a helium neon laser spot on downtown San Francisco. And lasers are used in all big construction works, any pipeline, gas line, any vertical or horizontal of the big buildings that go up here in Bangkok. They are aligned by means of lasers. And so the use of laser beams in the construction industry based on this directionality is universal. Also, because of the directionality, if you use a microscope objective, you can focus that light onto an area that is a linear dimension of a wavelength. Now, the wavelength of light is on the order of 1 micron, a millionth of a meter. Very small. To give you an idea how small that is, a human hair is 30 microns. So you can focus it on a spot that is much smaller than the dimension of the cross-section of a human hair. And you can focus it on an area of 10 to the minus 8 square centimeters. And you get all that light concentrated on that. You can write dots on a CD, and I don't think this will show up from the hall, but there are little marks which this dimension on the order of 1 micron, a millionth of a meter. And on every spot of 10 to the minus 8 square centimeters, you can make a mark with on a photosensitive material, which you can then treat chemically, and you get a little dip onto your CD player. And then you can read whether you have a little dip or you don't. If you have a dip, it's yes, one bit of information, and if there is no lactose there, had been, then it is a no. And you can read these CD discs out with a low power laser, even much lower power than the one I use here, semiconductor lasers, and every CD player has a little laser to read out these little dips formed by a bit of information depending on whether or not there was a light pulse. And then if you take an ordinary CD, it's easy to calculate that you can put 10 to the 10th power, that is 10,000 million bits of information on any CD disc. Because the area of the CD disc is like that, and you can put 10,000 millions of bits on that CD. And that is about equal to the total content of information in the Encyclopedia Britannica, 10 to the 11th. So you could put the whole Encyclopedia Britannica information on one or a few CD discs and write that information in with a laser and read it out with a CD player, also based on a little laser action. And then that information can be sent all around the world by another technological development which also uses lasers, and that is optical fiber communications. Again, because of the directionality of the laser, you can focus it on a very small spot, and the diameter of this fiber is smaller than that of a human hair, and the light gets trapped inside that because the index of refraction in the center is a little higher than on the edges. And these optical fibers are now used worldwide in our communication with all countries on this earth. And let me just briefly review the historical development of optical communication. This picture was taken in the street of Chicago in 1972. And it was the first optical fiber put underground to connect two telephone exchanges in Chicago. And in the big cities like Chicago and New York City, there was simply no more room. There were so many metal wires in the ground and other lines that they tried to make that much better by optical fiber communication. And a few years later, this is still only to 1982, that is the root system in the United States. And very soon thereafter, the first transatlantic optical fiber was laid between the east coast of the United States and England and France. And this is that cable-laying ship. And here you see a material a substation at the that's going to be at the bottom of the ocean to connect two fiber segments. People have now done away with these electro-optic amplifiers at the bottom of the ocean by simply using erbium-doped optical fibers which act like lasers in the fiber itself, and you can amplify the laser system without additional substations over a distance of 10,000 kilometers or more. So between the United States and Japan under the Pacific Ocean. And these laser-based optical fibers now produce our global communication system. This was the story of the first transatlantic optical fiber geography. That was in the early 80s. Now we have optical fibers everywhere. And this shows you just the growth of the optical fiber communication systems in millions of dollars. And of course it has still been rising. To give you an example of Thailand is connected to Western Europe by a system of 39,000 kilometers cable length. And it has 40 landing points in 34 different countries. And it only has 2 optical fiber pairs, and each can send 20 gigabits per second. But there is an optical system with an even higher capacity called the FLAG Atlantic system. FLAG stands for Fiber Link Around the Globe. Fiber Link Around Globe. This system contains 6 optical fiber pairs. They can send in each fiber 40 different wavelengths, which is called wavelength division multiplexing. And the capacity per fiber is therefore 800 gigabits. And since you have 6 of them, you can send 2.4 terabits. That is 2.4 times 10 to the power 12 bits per second. And that means that you can send the whole information of the Encyclopedia Britannica in less than 1/10 of a second between the United States and Europe. Such a system can support 200 million simultaneous telephone conversations. 200 million. And it could send simultaneously 450 high-resolution digital movies, if there was a need for that. So really, the world, our globe has become so interlinked by optical fiber communication, which have all these little erbium doped laser systems in the fibers, that the communication has improved so much that people can really communicate at length everywhere. And you all know it. You take up your cell phone and you can talk to anybody anywhere in the world, all because of optical fiber link communication. And I think that makes a unifying force in this world. Now, there are other laser applications, and they are used in heavy industry. This is an old picture of a 5 kilowatt CO2 laser. Now, those are used in the metalworking industry. They don't use pulse lasers, they use CW raw power, and they can drill hole in steel plates up to 1 inch thick. They can weld 2 steel plates together, and they are used both in the automotive and shipbuilding industries. And they are also used to give heat treatment to any part, like the cylinder walls in your car engine. You want those cylinder walls to be hard, so they last a long time, and they are strong. Now, it used to be that you make the cylinder walls hard by heating the whole cylinder wall and plunge it into cold water, which was called quenching, and then the substance became harder. But also the walls use their elasticity and their toughness. Now, what is the laser beam? You can melt temporarily a very thin layer on the surface, which then cools off very rapidly because the laser beam that speeds around melts it only for a very short time, and then it cools off again. And that is why you get a hard surface, but the toughness of the metal part is not affected, because the thickness it doesn't get heated. Only the tiniest surface layer gets heated. And so you can harden any gear of any shape with a laser beam and harden the surface without affecting the strength of the material part. Very important in the manufacturing industry. And here you see another example. Many of us here came by flying jets. A jet engine has turbine blades, which are made of titanium material that keeps its high strength at very high temperatures. But you can improve the efficiency of the jet engine by 1 or a few percent by drilling cooling holes near the tip. You do that by taking such a jet engine blade and putting a laser in there which drills holes in the strong titanium. Now, let us go from these high-power industrial applications to something much more subtle, and that is the human body. And here you see a picture of a human hair, and people start to machine the human hair with very delicate, sharply focused laser pulses. And you say, why would you do that? It's totally useless. But I use it as a demonstration of what a laser beam can do. Very low power, but very sharply focused to a few microns, and you could, if you wanted to, drill a hole in a human hair. But, of course, the real medical application is to use the laser beam in surgery. Because the light gets so sharply focused, and you take, say, a blue light, which gets absorbed by red living cells, you can cut through a blood vessel, and the laser beam is sharper than the sharpest surgical scalpel. The sharpest knife has an edge of about 10 microns. And the laser beam, as I say, it can be only 1 micron in diameter. So you get a much better defined cut, but also that you don't need sutures to prevent the blood vessels you cut from bleeding. Automatically, the surrounding is cauterized by the heat developed by the laser redevelopment. So laser surgery is much more precise and bloodless, and is a great improvement for many types of surgery. Of course, you have to be careful that when you use an ordinary light bulb, it gets focused on your retina, but you get a large spot. If you look into a laser beam, it gets focused onto this very tiny area of 1 micron in diameter. And while the laser light goes through the eyeball, and it gets absorbed by the red blood cells at the retina. And of course, you could do damage there. And in the early days, people got really hurt by looking into a laser beam. Now, the doctors use this damage on the retina to repair loose retina. If you have a tear in your retina, that's very dangerous and you may lose your vision. But you can reattach the retina by making damaged spots with a laser beam, and this can be done in a doctor's office. You don't have to be hospitalized. This is an argon ion laser, and the patient undergoes reattachment of the retina. The retina had a tear, and then you see all these white spots on both sides. Those are damaged tissue produced by laser spots. The surgeon carefully goes around both sides of the tear and the scar tissue reattaches the retina on both sides. And that is how you can repair detached retina with the laser beam. And as I say, the light goes under through the lens and the eyeball, but just at the point of the retina, where it gets focused, it can produce this scar tissue. Of course, you have to be very careful that you don't shine it on your fovea, your point of sharp vision. But retinas that get detached anywhere else, you can fix easily. Another example is, this is an 80-year-old man who had port wine stain, and his whole life he had this red mark on his face. Was inoperable before the lasers, but with a laser beam he finally got a normal skin on his face. And again, the action is simple. Port wine stain is due to the fact that your skin has many sections with too many blood cells, and so that's why they are red. But in between, there are parts of the skin which are normal. Now you take a laser beam that gets blue or green, that gets absorbed by the red parts more than by the normal blue parts. And here you see the temperature rises where it gets absorbed most, and those are the red parts. And there you let the temperature of the skin cells rise above the so-called coagulation temperature, which is the same as boiling an egg. You kill the proteins, you degenerate the proteins in the egg by boiling it, and here you do that coagulation by heating with the laser beam. And you dose the laser just right, that only the two red parts of the skin gets the high temperature, and the parts that are normal skin don't get above the coagulation temperature, so they stay healthy. And so by dosing the laser pulse and its duration, you can fix, eliminate the red parts of the skin, and so you could fix the port wine stain. Of course, also, because of optical fibers, you can insert those in veins and arteries, like here, and you can shine the laser pulse inside your body, too, and even to maybe coronary artery, and you can try to remove the plaque there to prevent heart attack from occurring. However, this is not yet medical practice. And the reason is that it's very hard. And it's not hard to remove the plaque, but it's very hard to avoid drilling a hole in the artery wall at the same time, which of course would be very bad. So this is not a medical procedure that is widespread used, although people have drilled holes halfway through the heart wall. Not all through, so you don't get a leak, but just by drilling holes in there, you form new blood vessels that can reactivate the blood supply to a heart wall by drilling holes halfway into them. Well, this is big, helpful applications of the laser beam in surgery, in medicine, in global communication, and of course in industrial applications, in the construction, energy, and so on. Let's now go back to the less peaceful applications, the military. The total laser market in the year 2000 was $6 billion US, and 80% was for civilian purposes, less than 20% for the military. So clearly, the lasers on balance are clearly being very beneficial to mankind. And the original idea of getting a missile defense with lasers is still only on paper, it's still not practical. Missile defense will not use laser beams in space. But laser beams are used by the military and I will give two generally examples. One is the laser rangefinder, and every tank in the world has now a laser rangefinder, so it can determine, shine a laser beam on a target, get the reflection back, and see how long it takes for that reflection to come back, and that gives the range of the tank to the target. And every Iraqi tank had that, every US tank had that, any Thai tank will have it. It's universal, laser rangefinder. Another one is target designation. That is that a person on the ground shines a laser beam on a target and you get the reflected light, which is received by an airplane or a smart bomb, and it homes in on the light of that particular color. You see, you use the distinguishing feature of the monochromaticity of the light beam, and the bomb or the airplane homes in on that target that is so designated. Now that's clearly a military application which in a way has saved lives, because instead of bombing at random in Vietnam to destroy a bridge, and they destroyed villages all around it, they finally used the laser beam, and then they finally hit the bridge right on in the first try with the target designation. So one has to be very careful in labeling all military applications as basically bad. You can argue about it. Is it bad or isn't it bad? But it certainly made the military applications more precise in these two cases. And then finally, I want to come back to emphasize the economic importance of the lasers. And here you see the laser development by this red light, which is dotted from this place on, because this slide was made in 1983. And it's compared with the light blue line, which is the sales of the US computer industry. And you see the two curves are essentially the same, except for a 17-year delay between the red curve. The laser was invented much later than the transistor, about 14 years later, and the industrial development of the lasers lagged by 17 years with that of the semiconductor computer industry. But the curves, except for that 17-year delay, looks very much the same. So in order to know what the laser beams are like now in the year 2003, you just have to look at where the blue curve is 17 years ago in 1986. And it's really remarkable that the laser development economically followed that dotted red line rather well. And so the development of the laser market and the semiconductor market are very similar, except for this 17-year delay. And once again, I emphasize that more than 80% of that market is for peaceful purposes and has benefited mankind. Thank you.
For a very inspiring talk. I believe a member of the audience now might have some questions or comments to make. We are collecting the piece of paper for questions. While we're doing that, I might start off with a question of my own. Professor, I am sure that your presence here has inspired all the lecturers and students here in the audience. What would be your tips to us in order to follow your footsteps to achieve the level of success that you are for the science and technology community in Thailand?
Well, The important thing is to have an interest in research, to be curious, and to try to find out things that are not yet understood or that you have observed and want to find the cause of. In order to do research, you have to have a certain amount of curiosity, and you have to have some questions that you either like to answer mentally and theoretically, or else by experimentation. And I think that is the basic thing, that you have to have a willingness to try to delve deeper in the understanding of what goes on in nature.
Thank you. Also another question from the audience. Laser has precise wavelength and high power, leading to nonlinear optics effect. Please give some comments on optical computing.
Well, maybe that's, we should go back to that question tomorrow when I give another lecture, and I'll do a little more science. Possibilities for lasers in computing. Of course, they are used already to store computer data in CDs and so on, as I already outlined. But there are more sophisticated things, which is called quantum computing. And with a laser beam, you could do new kinds of quantum logic, where it's not a bit yes or no, but it's somewhat in between. People talk about the square root between yes and no, and so on. And one needs very sophisticated control of photon states in order to make that quantum computing a reality.
Thank you. Just on that subject, another question from high school student. What do you see as the future of laser technology in this world?
Well, I think we'll see still more major advances in the field of medicine and surgery. This is still going on, and new procedures will come out. I forgot to mention one thing that's very widely spread, and that is to use laser ablation of your cornea to correct vision, so you can get sharp vision without using glasses. And one uses laser pulses steered with a mirror and computers to abrade a little bit of your cornea, so you get the correct correction for sharp focusing on your retina. And this is a past example. I don't know enough about medicine, but I know that the medical world is using lasers for all kinds of new procedures. And there is a journal especially devoted to lasers in surgery and medicine, international journal, which comes out with 30 new articles every month. And I haven't followed it all, but I can be assured that the medical world pays a great deal of attention to applications of lasers.
Thank you. I think we'll have time for a few more. Thank you. This is from more advanced physicist community. How is a laser beam affected by gravity? For example, of a planet or of a black hole?
How is a laser beam affected
by gravity? By gravity.
Very little. The light is affected by gravity, and we know that from the distortion of distant stars which are behind another galaxy, and people can see gravitational images of star systems behind another galaxy. And so light beams get slightly affected by the gravitational field as well. And of course Einstein used these ideas in formulating his general theory of relativity. Now, laser beams have been used to test these predictions of Einstein, and they have measured the variation of the light frequency with the gravitational field to high precision. And laser beams are now also used to try to detect gravitational waves. This hasn't succeeded yet, but there are two three or more very big projects. One is called LIGO, Laser Interference Gravity Detector, in the United States. There is another system in Europe. I think there is one in Japan and in China. And people eventually hope to detect the emission of gravitational waves by a supernova star that emits this type of gravitational radiation.
Thank you. Another one is a question concerning holograms. What role will holograms play in the future?
Well, I wish I could answer that question. Holography is very interesting to see, and you get these beautiful three-dimensional pictures. And they have been used at expositions and so on. But I haven't seen any really large-scale application of holography yet. I hope it comes. But I have to leave that to the engineers.
Okay. This may be another question which that students require some clarification. A DVD is the same size as a CD. Then how can it store more information? How can it store more bits?
Well, you can store more bits if you go to shorter wavelengths. And recently, in high-definition CD, they have improved the number of bits you can store on a CD by a factor of 4, because you use the wavelengths of light, which is a factor of 2 smaller. You use it in the UV, and then you have factor 2 in this direction and that direction, so your focal spot gets 4 times smaller. And that is how you can put 4 times more on a high-definition CD by using laser light at a shorter wavelength devices. And this naturally led to the application in the laser field. I should warn you, I never invented any laser myself. That's Thomas and Chalhov and Mayman and so on. But I recognized that the same ideas of pumping would hold in the optical region. And I also realized that once these lasers yielded these higher light intensities, that you could use that to study the field of nonlinear optics. That is just as a vibrating string. If you pluck it too hard, you get overtones, or an organ pipe, if you blow too hard, you get distortion of sound. You get a new science, the science of nonlinear optics, by looking at the optical properties at high light intensities. Then the electron oscillators behave in a different way, and you get all kinds of nonlinear optical effects. So that is briefly how I got started in nonlinear optics.
Okay, we have many questions. This is different to any other lectures that we had. I think a lot of students here are interested in laser because they've seen laser since they were very young. Another one is a question about war, because we talked about peace just then. Is it worth the investment of $9 billion in the missile defense project?
Well, that is another question. Most of the 9 billion won't go to lasers. The $9 billion goes to other types of interception, kinetic energy weapons and so on. But it just shows you that it is very hard to hit an intercontinental missile that's coming its way. Very difficult. And people were overly optimistic in the Cold War that they could do it. President Reagan's strategic defense initiative never delivered a strategic defense. And now we are not talking about strategic defense. Now we are talking about just trying to shoot down one rogue missile from some nation or a terrorist organization. And we still can't do it. And how many years will we have to spend $9 billion to keep trying? I don't know. But it certainly is not money spent on much on lasers. People try other avenues mostly.
Thank you. To the final question for this session. Could you give advice to our young students and lecturers on how to think like a Nobel Prize winner? What do they do?
I'm sorry to say that was the same question I got asked in China and Japan. And there is no particular road that leads to Stockholm. There are many different roads that lead to Stockholm, and each Nobel Prize winner has followed a different road. But the point is this, there are even many more roads that do not lead to Stockholm. And you may just as well take one of those. The important thing is to do something that you're interested in. Try to answer a question you'd like to obtain an answer for. And then, maybe with a lot of luck, it may lead to Stockholm, but the chances are it will lead you somewhere else. But that is just as good. Thank you.
Thank you. Ladies and gentlemen, I'm sure you would like to hear more from our guest speaker, Professor Bloembergen. We will have a special lecture given by Professor Bloembergen titled Science and Global Communication based on Optical Science and Technology tomorrow, the 13th of January at 9:30 till 11:30 a.m. at the conference room, second floor, building 4, Faculty of Engineering, Chulalongkorn University. And now, once again, may I invite Assistant to the President, Professor Chulalongkorn, to present our honorary lecture with a gift as a token of our appreciation. Ladies and gentlemen, our special lecture has come to an end, and all of you are cordially invited to some refreshment in the reception room. Also, I would like to have a few announcements to make. Tomorrow we'll have a special lecture by Professor Ferry Mura in the same program, Bridges Towards Culture of Peace. We'll start at 14 hours. Also, I would like to express my thanks to our translator for the headphones today, Dr. Prodran Hitsaton from the Faculty of Engineering, Department of Computer Engineering. Thank you very much and hope to see you again very soon. Thank you.
ขอเชิญแขกผู้มีเกียรติที่ได้รับจดหมายเชิญไม่ว่าจะจากทางสำนักงานวิราชกิจธนาคารกสิกรไทย ทางคณะวิศวกรรมศาสตร์คณะวิทยาศาสตร์นะครับเชิญรับประทานน้ำชาร่วมกับผู้บรรยายนะครับข้างหลังห้องนี้นะครับแล้วก็ขอประกาศอีกครั้งหนึ่งว่าพรุ่งนี้จะมีการบรรยายพิเศษโดยศาสตราจารย์ดร.นิโคลัส โบลเบอร์เกนนะครับในเรื่องวิทยาศาสตร์และการสื่อสารยุคโลกาภิวัตน์ที่อาศัยวิทยาศาสตร์และเทคโนโลยีเชิงแสงนะครับจะจัดที่ห้องประชุมชั้น 2อาคารเจริญวิศวกรรมหรือตึก 4นะครับจะเป็นอาคารสูง20 ชั้นที่คณะวิศวกรรมศาสตร์นะครับจุฬาลงกรณ์ซึ่งจะเป็นคณะที่ติดกับหอประชุมเนี่ยนะครับก็งานจะเริ่มพรุ่งนี้ตอน9 โมงครึ่งนะครับก็ขอเชิญท่านที่สนใจทุกท่านเข้าร่วมฟังการบรรยายพิเศษต่างๆด้วยนะครับขอบคุณครับ